Greetings, my fellow humanoid dwellers. I create videos on technology and other random things. If you like this video, you might like others. If you don't like this video, you still might like others. Consider subscribing to my channel or checking out my Patreon page. If you already subscribe, hit that bell. In today's video, we're going to go over RC time constants. RC time constants are resistive capacitance time constants. Using the value of the resistor and the value of the capacitor, you can calculate an RC time constant. The reason I'm going over RC time constants now is in future videos I'm going to start talking about transistors. And one of the experiments with the transistor is to make an LED blink. So far we have dealt only with analog components. We have not got into things like digital ICs or anything digital. And we're going to use analog components to make a blinking light. If you're familiar with Arduinos or Raspberry Pis, some of the first experiments you do is make a light blink, but that's using digital technology. We're going to do it with analog technology. And so a basic understanding of RC time constants will help you understand when we get into transistors and we make a light blink. It takes 5 time constants to charge a capacitor. And capacitors, if you remember, are measured in farads. 1 millifarad is 0.001 farads. 1 microfarad is equal to 0.000001 farad. This is important to remember when you're calculating out the RC time constant. 1 time constant is equal to capacitance times resistance. Each time constant gets us approximately 63% of the remaining voltage needed to charge the capacitor. So the first time constant gets us 63% of the way. After the second time constant, we're 86% of the way. After the third time constant, we're 94% of the way. After the fourth time constant, we're 98% of the way. And then after the fifth time constant, we're 99% of the way. That's why they say it takes 5 time constants to completely charge the capacitor. It's not fully charged, but it's 99% of the way. In our example, we're going to use a 1000 microfarad or 1 millifarad or 0.001 farad capacitor. And we're going to put that in series with a 10,000 ohm resistor. And if you take those two values, multiply them by each other, you get 10 or 10 seconds. So that means each time constant is going to be approximately 10 seconds. We're going to run our circuit on 10 volts. So after 10 seconds, we should expect to see 6.3 volts. And after 50 seconds, we should see it approaching 10 volts. I'm going to switch over to the simulator now and show you an online example with not so exact results because it is a simulator. But then we're going to switch over to a live circuit and show you actual measurements. The circuit I have set up, I'm using a power supply, so I can set it exactly at 10 volts. We'll feed the voltage up, across here, down through this switch, which right now is switched over to go to ground. But when we switch it over to here, it will be to 10 volts. Then it will feed down through the resistor, which I have set at 10,000 ohms or 10K, through this wire, through the capacitor, and back to ground. One of the reasons I put this switch in is so after it's completely charged, we can flip the switch and then we can watch it discharge and see if it operates approximately the same. I have a stopwatch set up so we can keep track of it. The plan is to flip the switch and then quickly go over here and start the stopwatch. I'm going to stop the stopwatch when this hits 6.3 volts and see how close we are to 10 seconds. And there, I stopped it at about 6.3 volts, and it took about 10.78 seconds. Now we're going to go ahead and let it charge all the way to 10 volts, and we're going to watch it discharge. We're going to see if it goes down to approximately 3.7 volts in 10 seconds. And then when it's all done, we'll go ahead and charge it back up, and we'll time it to see how long it takes to get to 10 volts. Now I'm going to reset the timer. I'm going to flip the switch and start the timer. .64 seconds, which is about what we would expect to see. Okay, now I'm going to reset the timer. And this time we're going to continue to watch the voltage until we hit 50 seconds on the timer. But remember, in real life, the components will dictate what happens and may vary the results depending upon the tolerance of the resistor and the tolerance of the power supply. You'll see in the real example that the power supply isn't exactly right on. Also, if you think back to the last experiment, this should make sense. As the voltage changed across the resistor, the current changes, and that's what decides how fast the capacitor is going to charge. Now we're going to go ahead and switch over to a live circuit, and we'll see if we can repeat the results. In this circuit, I have the same values of capacitor and resistor. I have one meter measuring the supply voltage and another meter measuring what's across the capacitor. As the capacitor charges, I'll hit pause when I get close to 10 seconds. It looks like it's pretty close. At 9.8 seconds, I had 6.3 volts. Now we're going to go ahead and let it go and see what happens when we get to 50 seconds. We'll stop it again. Now here it's not quite as close. There's a little bit more of an error, which is really what I would expect to see. I would not expect to see perfect results. For the final test, we're going to go ahead and switch the resistor over to ground, so we have a path for the capacitor to discharge. See if we can get around 3.7 volts after 10 seconds. Well, that's about it for this video. Thanks for watching.